All right, well, our topic today is about as far as we get in like dense mathematical theory in this class, which is not very deep. But this is where we talk about P versus NP, which is something I've heard about for years, and I only understand a little bit now after reading this chapter and some articles. So that's the concept of computational hardness, which is much easier to understand in practical cases. And it's going to turn out that the abstract mathematical argument about P versus NP, in fact, doesn't really matter from a practical point of view. It's worth knowing about, but as you'll see, the realistic concerns to make a cryptography system are different. So computational hardness is really important. And this is where you decide whether a problem is hard or not. And what you want, of course, is you want to have a cryptographic system where breaking into it without the key is hard. So you try to define what hard is. And here, let me just clean up something. I got something weird going on here. All right, that should do. All right, so, and the idea here is instead of measuring exactly how long it takes for a particular attack to get through, you get a measure of how rapidly the difficulty increases as the size of the problem increases. So if you're going to have an array of n elements and you're trying to find something in there, then you can just loop through all the elements to see if you find it. And if you're going to find it, you'll find it on average halfway through. But if you're not going to find it, you have to go all the way to the end. So the expected amount of work is something like n over 2. And so they call that linear in n. If I double the size of the list, I double the running time it will take to do the problem. And that's what we consider an easy problem. That's linear complexity. So linear is one, you can have linear logarithmic, an efficient sorting routine. An inefficient sorting routine would be n squared complexity, but an efficient one will be n log n complexity, which is grows a little faster than n to the first power, but not as fast as n to the second power. Now, brute force key discovery, we've talked about, if n is the number of bits in the key, then to try every possible key, that would be 2 to the n keys. So you'd have to do something like 2 to the n calculations, and that doubles every time you add 1 to n, so that grows very fast. And quadratic time is another thing you see where it just grows as n squared. All right, so in general, here's what they look like. This is linear, this is quadratic, and this is exponential. It's really much, much faster. As n gets big, it gets bigger much, much faster. So the general categorization is anything polynomial is considered easy. If it goes n squared, n cubed, n fourth, or anything like that, this does not really rise all that fast. But things like 2 to the n or n log n are considered hard because that grows much, much faster. So a large problem will just get extremely difficult to solve. And if you think about it from a design point of view, if anybody's able to crack your key cryptography, you could just make the key a little bit longer and it would no longer be able to crack it. Whereas here, you'd have to increase it by a larger amount. And here's an example of that. There's quadratic, and here is 2 to the n, much, much faster. And I think that's n to the log n, yeah, in between. So again, much, much faster. So you can define your complexity classes, and they define it by the time complexity is mostly what we consider. You could worry about memory too, but the main thing we talk about is time. So if the time complexity is the order n squared, then the amount of time it takes depends on the size as the square. So if you double the size of the problem, it will take 4 times as long to solve. But 2 to the n, if you add 1 to the size of the problem, it will take twice as long. So it's much, much, it grows much more rapidly. And you can also talk about space complexity the same way. You could say how much memory it's going to take. That's another way to look at it, if you make a memory-hard algorithm. But most of the time, people consider the time-hard algorithms. So here you get the general category. So P is the class of all polynomial time algorithms. So these are things that can be solved in polynomial time, and those are considered easy or practical. NP is the class of all non-deterministic polynomial time algorithms, and these are problems where you can verify a solution when you find it in polynomial time, but there is not a known algorithm, there may not be a known algorithm to find the solution in polynomial time. And the general belief of everybody is that P are the easy problems and NP are the hard problems, but nobody has ever been able to prove that mathematically. The problem is you don't know if the NP problems do not have a polynomial solution, or if it's just that you haven't found it yet. And no one's been able to find a way to prove that. So these are problems where we believe there is no easy way to do it, but we cannot prove that. So here's some NP problems. So recovering a secret key with known plain text. This is NP because if you know the key, it's very easy to verify the key is correct. You decrypt it and see if you get the plain text. But finding the key without knowing the key is very hard, but that's a different problem. So there are problems outside NP and P. And we talked about this before. If you consider the perfect cryptographic system, the one-time pad, if you have some ciphertext and you do not know the one-time pad, if you try every possible one-time pad, you will create every possible plain text message, and you have no way to tell which one is right. So this is not even a mathematical problem. It's sort of a logic problem. There is no possible way to do it given any amount of time without more knowledge. You simply have no way to reverse it. So this is very hard. It's harder than P or NP. And another thing is the one I've mentioned before. If you want to prove that there is not a fast algorithm to solve one of the NP problems, that's proving that no solution exists. And that is very difficult. The obvious way to do it is to try all possible solutions and prove that none of them work, but that's not practical. And this is the one that people have been struggling with for years, and they haven't been able to prove that the NP problems are really hard. It is possible that they are in fact easy, and we just haven't found the easy algorithm yet. So the NP-complete problem are generally considered to be the hardest problems in the class NP, the ones that are most difficult, and it turns out there's a series of these that are all mathematically the same. If you find an efficient solution for any of them, you can solve all the others. So here's some famous examples. The traveling salesman problem is famous. If you have a set of endpoints on a map, and you just want to find a route that visits all of those with the minimum total travel time, this turns out to be very difficult. The clique problem is where you have a set of points connected by edges, and you're trying to find a subset of those points that have a single path to every other member of the subset. And then the knapsack problem is where you have a bag that can only hold so much weight, and you're trying to choose the objects to put in the bag to optimally fit the maximum amount of value. You have an object with, say, a price and a weight, and you're trying to get the maximum price for a certain amount of weight. And these are all they sound different, but they're not different. They're all mathematically identical. Here's the clique problem. You have a series of nodes connected by other nodes, and you're trying to find which nodes are fully connected. And it's this group of 4 in the corner are fully connected. There's a single path going from every one to every other. These others are only partly connected. So finding out what part of such a graph is a full mesh is the question, and that turns out to be very difficult as n increases, like they all do. So now, some video games are NP-complete, apparently, like Super Mario Brothers and such. They say, and some are even harder. There is a group of problems called NP-hard, which may be even harder than the NP-complete ones, but the only thing they're able to prove is they are at least as difficult as the NP-complete ones. They might be so hard that they're actually not in NP, that you can't even verify the solution. So if you could solve the hardest NP problem, the NP-complete ones, in polynomial time, then you could solve all NP problems in polynomial time, and then NP would equal P. And no one has proven this yet. There's a $1 million bounty for anyone who proves whether this condition is true or not. It's famous in computer science. If P equals NP, then none of these problems are actually hard. It's just that we haven't found the right efficient solution yet. And if that was true, that would destroy all our cryptography. Then there would be a way to find the key efficiently. Most people think this is not true because we have this belief, we've all learned mathematics and there are hard problems, and they really seem hard. It seems like it's not that we're just smart enough, it's that they're really hard. But anyway, that's the question. Here's what most people believe the situation to be. NP is a big group, and P is a small subset in here of the problems that are easy. The NP are hard problems, and the NP-complete are the hardest problems. This is what we believe to be the case, although we have not been able to prove it yet. And so, it turns out the factoring problem and the ones we use in cryptography are not the NP-complete ones. They might seem like the most logical ones, but it turns out they have disadvantages, so less difficult ones in here in the population of NP are the ones we actually use in cryptography. And by the way, quantum computers add more dimensions to this. There's now a group of problems that are solvable on a quantum computer, but not on a classical computer. And so this diagram of PNP, and then Now, a BQP is another possibility, and the people that do this abstract mathematics are trying to decide how quantum computers fit in this system. Anyway, here's the XKCD making a joke about it. If you have a list of objects and prices, then if you tell them I want an exact this many dollars amount of appetizers, that is the knapsack problem. What combination of these will add up to just that total? And it is more difficult than you think. Of course, for a very short list like this, you can solve it by brute force, but it turns out to be surprisingly difficult to solve in the general case. So if breaking a cipher were NP complete, then you would think that would be the strongest cipher. Then you would have the hardest possible NP problem to find the key if you don't know the key. But the problem is, NP-complete problems are easy in certain specific cases. And so what we use is problems that are probably not NP-hard. So there was an attempt to use one of the NP-hard problems called learning with error. This was the basis of Google's proposal for a quantum-safe algorithm, and I was trying to add it to this course. I found some instructions, and then it fell in the third round. I thought it was going to win because I had faith in Google, and I learned how to do it a little bit, and I was writing hands-on project with it, but it's gone, so forget that. When they finish this process, then I'll try writing hands-on process for whatever the winner is. But anyway, that was an attempt to use an NP-hard problem, the only time it's ever been used in cryptography, and it turned out to be weak, and they found a way to hack it. So there's currently no NP-hard problem used in realistic cryptography. None of them have turned out to really have the properties you need to make a successful cryptographic system. So the factoring problem, of course, is one of the ones we really use. We all know this. This is what RSA uses. If you have a large number n, that's the product of two primes, p and q, finding those from n is a hard problem. In practice, it is in NP, it is not NP hard, but it is in NP. There is no known polynomial solution for that. So now the prime numbers are the numbers that cannot be divided evenly by any number other than themselves and 1. So 1, 2, 3, 5, 7, and 11 are prime. 9 and 15 are not prime. They're composed of smaller numbers. So if you wanted to solve this problem, the simplest algorithm would be just try dividing it by all the numbers up to n minus 1 and see if any of them divide evenly. Then you'll have found this will, of course, work, but that would take 2 to the n calculations. If n is the number of bits in n. All right. So that would be a hard problem. It'd take if you had a 256-bit n, it would take 2 to the 256 operations to do it that way. So that would be a very an impossible task and a good secure system, if that's what people had to do to get in. But this is, of course, not the best algorithm to use. For example, you could try only the prime numbers from 2, and you only need to go up to the square root of n. One of the factors has to be below the square root, and the other has to be above the square root, so you don't need to try any higher than that. P, the smaller number, must be in this range. So now you're trying a much smaller number of guesses, so this is only 2 to the n over 2 over n, which is hard, but easier. Now it would only take 2 to the 120 operations to crack a 256-bit n. And remember, about 100 bits is enough that the problem is impossible, and you're fine. So this would be secure enough. But it turns out that there's an even better algorithm called the number sieve, and that's even faster. So for a 1024-bit n, you can solve it in 2 to the 70 operations, and 2 to the 90 will take you to 2048, and that's why the current recommendation is 4096 bits to get 128 bits of security. So that's the largest known algorithm, and you observe the situation here, which is the problem. It's not a provably hard problem. In fact, nothing is, because we haven't even proven that NP is not equal to P, and so we don't know that this is the best algorithm, and in fact, there's a better one. And we don't know that this is the best algorithm. There is, in fact, a better one. For all we know, there's a better one, and these numbers will come down, and your supposedly secure system will get cracked because there's some way to get this down to like 2 to the 30 or 2 to the 40 for 4096-bit keys, and we have no mathematical proof that that is not true. We're using it because we haven't found that yet, and we don't know what else to do. So here's the experimental results. In 2005, they cracked a 663-bit n was factored, and in 2009, a 768-bit n was factored. So people imagine, that's been 22 years ago. Well, that's been like, what, 12, 13 years ago. So people imagine that a highly powered adversary like the NSA can probably crack a 1024-bit key right now. We don't know that, but we aren't that far from it. So therefore, people think 1024 is probably not secure if your adversary is a nation state with the kind of power to do that. So is factoring NP complete? and nobody knows. No polynomial time algorithm is known, so it appears not to be NP. It's not an easy problem, and you can easily verify a factor when it is found, so it's definitely in NP, and so they think it's probably easier than NP complete, but none of these things have been proven. Now, quantum computers change everything. They can factor it without doing so many calculations at all by carefully designing a pattern of gates to solve one prime number. And this one here solves this equation, 7 times 13 mod 15. That's what this gate solves. And they haven't made quantum computers that can solve anything difficult. They're just up to numbers like this, like 15. So they've proven in principle that they can solve it, and the difficulty does not scale so fast. So when you have high enough quality quantum components, you should be able to crack RSA keys of any length. But those are not available yet, and they probably won't be available for 10 or 20 years. But in principle, quantum computers change it, and the factoring problem will become easy, and therefore RSA will just be shot. Making the key longer will not help. So you start from a problem that's assumed to be hard, then this is all you can do in cryptography. Since you can't really prove exactly how difficult problems are, you can prove that one problem is related to another problem. That's what you do. So you can prove the factoring and discrete logarithm problems are well-defined problems, and you can prove that a system is as difficult as factoring, or as difficult as the discrete logarithm problem, and that gives you some confidence in them, although, as we were just saying, perhaps you shouldn't have so much confidence. And I think I forgot my hat. I'll try to put the coat back on. Anyway, all right. I've got many, many coats and such. But haven't found the right solution for teaching in here. All right. Anyway, so, all right, so the discrete logarithm problem is the generalization of RSA, really, and here's how it works. You have to have a group. Now, a group is a set of elements and an operation that obey certain axioms. The most common group you use is Z star P, which is numbers from 1 to P minus 1, where P is prime. So Z star 5 is 1, 2, 3, and 4. The numbers up to, but not including, the prime number at the top. Now, the operation, here's the 4 things you have to make a group: closure, associativity, identity, and an inverse. And so closure means you have your operation, like multiplication or addition or something, and anytime you combine 2 elements of the group, the result is still in the group. They talked about this a long time ago. This is why we use modular arithmetic. So if I feed in a byte of data and encrypt it, I get 1 byte out. It doesn't become bigger. Associativity means you can do operations in different orders. You can multiply x times y and then z, or you can multiply y times z and then x, and you'll get the same answer. So that's true of all simple operations that we use here. The identity means there is an identity element, so that when you multiply it by any member of the group, you just get back the member of the group. That's important. You have to have an identity because you need an inverse. And of course, we're going to use this operation to encrypt something, and we're going to want to be able to decrypt it. So we have to be able to find an encryption key D and an encryption key E and a decryption key D that will undo it. So there needs to be some combination of some number that gets you back where you started, and we need to be able to find the inverse. So x times y is y times x, and it equals the identity. So that would mean y is the inverse of x. And so if you encrypt with x, you can decrypt with y. That's the idea. And I can see how these are true of the RSA multiplication and exponentiation that we've been using, and you can make a more general situation here where you do not specify exactly what the group is and exactly what the operation is. Anything that fulfills these rules will do. So there's commutative groups where if you have x times y equals y times x, that's often the case. And you have cyclic groups, which are what we're going to do. Cyclic groups have a generator. There is at least one element g, which you can just multiply by itself, g1, g squared, g cubed, and so on, and you'll get all the elements by just raising it to a power. So those cyclic groups are the most useful for encryption. And so now we can define the hard thing. The hard thing is if I take the generator to y and I get x, and you know x, finding y is the hard problem. And this is analogous to factoring. So that's the problem. So that's the issue here. And then you can prove this problem is about as hard as factoring, and factoring was considered very hard, and RSA was trusted for a long time, and it's still used today, but we're going to have to stop it if you ever get our quantum computers working well. Anyway, so that's the generic discrete logarithm problem, and we're going to talk about it. So anyway, it may seem a little abstract, but we'll be doing some real hands-on with it eventually. So things that can go wrong. For example, if somebody found a fast algorithm to factor numbers, that would ruin it. And by the way, like I say, that is happening if you had quantum hardware. Quantum hardware is going to be the fast algorithm to factor numbers, and that will trash it. If somebody proved that P equals NP, that might ruin everything, but it might not, because even if P equals NP, it doesn't matter unless you can find those fast algorithms. This is something mathematicians often do. They prove that a solution exists, but they can't find the solution, and therefore it doesn't really matter. So if factoring is easy, by the way, sometimes factoring is easy anyway. For example, this 1024-bit number is easy to factor because it's 641 times some other numbers. If it's the product of several primes, not just one, and one of them is small. So you can just start at 1 and count up until you divide it by something, and then it gets shorter, and then things get faster. So if you have a number with a small prime factor, then you can factor it pretty easily. And if P and Q are not random, and you have some idea where they are, then again, you can just look there, and we had some problems we talked about before like this. Or if you have some information about P and Q, or if n is small, like 128-bit RSA, all these are easily factored. So not all factoring problems are hard. OpenSSL, for example, will let you make keys as short as 31 bits. It'll do it. Of course, that key is easily cracked and not secure, but the program will let you generate them. And the original RSA paper that came out in 1978 recommended 512-bit keys, which are these 200-digit numbers. They figured that was enough that it would take a million years to crack, and so everything is fine. But that's because the computers in 1978 were a lot slower. So 512 was considered strong enough then, but we've gone up from then. Like I say, now you should have 3072 or 4096 to be safe. And there are other problems. Because of the United States' attempt to prevent enemy nations from getting cryptography, we outlawed exporting cryptography and created these weak systems for export like Microsoft Windows version N. And those used low-quality cryptography with short keys that the NSA could crack. And once they're out there, if you want to put up a website and you want to serve customers using that old software, it has to be possible to downgrade your encryption so the encryption available on those machines. And therefore, there are attacks that involve tricking the server into serving the old weak encryption, which you can crack. And they call that the logjam attack. I can intercept your traffic in the middle and change your traffic so it tells the server that you're using this old weak computer, and it has to downgrade the encryption, and therefore you can get it down to a crackable level. And of course, state-level adversaries, as we say, can probably crack a 1024-bit key, and it turns out that a whole lot of servers are using the same prime numbers. And if those can be found, a whole lot of that stuff would be crackable. And there is some evidence that the NSA has in fact done that. For this cryptographic system, they're still using 1024-bit RSA. And so here's some of the information there. They found a lot of servers vulnerable to logjam, and a whole lot of them vulnerable by using this common 1024-bit group, which might be crackable by a nation-state adversary. So they found a whole lot of encryption that was actually in use was vulnerable to these attacks. Anyway, so let's take a look at a Kahoot. Google. All right. Chapter 9. right. All right, so what's the hardest problem? The exponential is the hardest in that group. Linear logarithmic is slower than exponential. That's like n log n. All right. All right, which one of these are the easiest? Here are the easy problems, the ones you can solve in polynomial time. All right? All right, which one is the knapsack problem? That's NP complete. The hardest NP problems, or so people believe. The NP hard problems might even be harder, and they might actually be outside NP. And which problem is factored? What group does it fit into? It's NP. It's not NP hard or NP complete. Those turn out to be undesirable. It's just in NP. All right, so how long should an RSA key be to give enough security these days? All right, 4096 is what you need these days if you want 128 bits of security. All right. Good. Stop this recording.